Okay, it's my pleasure to share today a different application from a Frontier Laboratory product, which is called a microreactor. Now, I'm going to share about the use of single microreactor for rapid catalyst screening. So Frontier Laboratories has developed two kinds of microreactor. The one is called a single microreactor, which is shown in the left side of the image, and the other one is called the tandem microreactor, which is basically having two two microreactors put together. So the tandem microreactor actually helps us to handle a solid sample like biomass to treat it at high temperature. Subsequently, it can be introduced to the catalytic pyrolysis for um, specialty chemicals or value-added products. But today we will show the application of single microreactor for a rapid catalyst screening. So here is a simple system diagram for single microreactor. As you can see, this is the furnace body, and we have a PY tube, the quartz tube, inside which the catalyst is filled, and both sides it is capped with the quartz wool, and we have a cooling gas in and out, which allows to cool down the furnace for different temperature conditions. And in single reactor, we can introduce a sample as gas or liquid, and you can use this carrier gas module, by which you can use different reaction gases, as well as you can have a carrier gas for your GCMS application. How we see it as an online system, because the outlet of the microreactor is directly connected to the GC system through the inlet, so which allows you to monitor or study the chemical change that is happening during the temperature treatment inside the reactor. So you can do a continuous monitoring as well as a stepwise heating and GC-MS separation-based analysis, so which I will explain it later. So the system diagram is very simple. So the point is, this microreactor can be easily attached to a GC-MS system, which allows you to do the in situ monitoring of the reaction system. In today's application, I'll be showing two sort of application. The first one will be based on the Fischer-Tropsch synthesis, and the second one will be the catalytic conversion of ethanol into ethylene and butadiene. So let me initially discuss about the Fischer-Tropsch synthesis. As you know, Fischer-Tropsch synthesis is basically converting the mixture of carbon monoxide and hydrogen, it's called syngas, into sulfur-free hydrocarbons. And this synthesis has attracted much attention from the academic and industrial communities, because this is seen as a green kind of fuel, and it receives economic and ecological importance. So for this Fischer-Tropsch synthesis, you can use the syngas that is produced from a biomass conversion. So, and it can be classified as a renewable energy source. So in Fischer-Tropsch reaction, basically you are trying to convert the mixture of carbon monoxide and hydrogen into olefin or gasoline or diesel, so different hydrocarbons. So this product choice or preference can be easily influenced by the use of different type of catalysts. So we just want to show how the single reactor can be used for evaluating such catalysts. So Fischer-Tropsch synthesis catalyst. So there is a continuous effort to develop new catalysts with improved properties, which can answer today's challenge for alternate fuel supplies. So from the literature, you will see that cobalt-based FTS catalysts are claimed to have advantage of higher conversion rate and higher selectivity to paraffins. And particularly, it can give you the longer life or longer lifespan performance if your synthesis gas are not really contaminated or if it is a pure form. So similarly, the iron-based catalysts have got higher selectivity for olefins, particularly if your desired product need to be C5 plus and so on. And this will also show the lower selectivity for methane and higher tolerance for sulfur compounds. In addition, Fe-based catalysts can be operated in wider range of temperature and wider ratio of this hydrogen and carbon monoxide, and which is important when you are using the biomass gasification products. Similarly, there is another catalyst, ruthenium, which is also gaining a lot of interest in this FTS synthesis. It's because ruthenium is very active FT catalyst, as evidenced by the fact that it can be operated at low temperature, and it is much more active than nickel, cobalt, and iron. It is a very versatile. That means at high temperature, it is useful for methanation, and at low temperature, it produces large amount of wax in the low polyethylene range. So the objective of today's webinar is to demonstrate the use of single microreactor to study the effect of selectivity for C3 and C4 olefins in Fischer-Tropsch synthesis with the use of a ruthenium catalyst. Further, we will give a glimpse on using this single microreactor for catalytic conversion of ethanol into ethylene and butadiene. So let me explain the experimental condition for real-time monitoring. When you want to set up the experiment for real-time monitoring, so you have your microreactor attached to the GC inlet, and from the inlet we use a deactivated tube, which is more like a transfer tube or transfer line to transfer the gases into the mass spectrometer for looking at the nature of these gases or the products. Inside the reactor, there's a quartz tube which comes with the 3 mm ID, and you can catalyst bed of this 4 centimeter, and you pack the quartz wool at the bottom and top. So here is the summary of the reaction condition. So we use syngas of hydrogen and carbon monoxide, the ratio of 2, and the total flow rate is 9 ml per minute. And we are using the 5% ruthenium alumina mixer, and which is actually obtained from Chemcard Corporation, and the size of 50 microns. And the catalyst bed is actually 90 milligram in mass and total of like 1.5 centimeter. And the reaction temperature, actually we do a program heating. So starting from 100 with a ramp of 10 degree per minute and heat it up to 400. And this reaction is done at atmospheric pressure. So for the measurement, yeah, as I said, we use this deactivated EGA tube, and the GC injection temperature is 300 and oven temperature is 300, and the scan range is 10 to 200, and scan speed is 0.3 scan per second. And this is the set of data you will get when you run this single microreactor and attaching it to a GCMS. So what you see here, the change of concentration profile of carbon monoxide. So that means it allows you to see at what temperature you see the decrease in carbon monoxide, and also the product of different ratio depending on the type of the working temperature. So the first peak shows the methane formation, which is obvious at 300 and above. And again, water as intermediate is seen also from 250, and this also keep increasing when the temperature is above 300. And carbon monoxide, the carbon dioxide also is forming when you hit the catalyst at like 300 and above. So as our interest is olefin of C3 and paraffin of C5, so these are mainly formed in the temperature range of 200 to 300, and mostly it's around like 250 degree temperature. So this information can be obtained with this single reactor, where we use just a transfer line of this deactivated tube. If you want to have more detailed analysis of these fractions, then probably you have to use a different setup. So where we call it separation analysis. In this case, yeah, the furnace, the micro furnace or the single reactor is same, but we have some additional accessories called a selective sampler and also the cryo trap to retain these low volatile compounds. So the selective sampler allows you to transfer the each fraction of this different temperature condition, which is done through this stepwise heating. Then the other difference is we use a GC column instead of simple transfer line. So these are the two major difference in terms of the instrument or the experiment setup. So we have selective sampler and cryo trap, and we use GCMS column. But the catalyst bed is same like what we have shown it for the continuous monitoring. Okay, in this experiment, we have done stepwise heating from 180, 190 until 320. That means you are able to collect the detailed GCMS analysis of the products formed at each of these temperatures. And this is what you are seeing in this slide. So at 180 degree, you can see still the carbon monoxide is the dominant peak, and which is slowly like reducing as we see the temperature rise. And particularly, yeah, when the temperature is like 220 and above, you can see the formation of these olefins and also the other long chain hydrocarbons. And as you go above 260, then you can see these olefins products are disappearing, and you see the increase in carbon dioxide and water. So this is what something we have seen in this continuous monitoring as well. So here it cannot give you the kind of absolute concentration analysis, but with the GCMS, uh, you would be able to look at the absolute concentration by calculating the peak area or the peak height of these different peaks. So this is just the expansion of the one of the peak that is produced at 240. So as our interest is C3 and C4, we can see at 240 the C4 compounds are more predominant than the C3, but C3 is there, but their concentrations are much smaller. So this is what the stepwise heating followed by the GCMS analysis will give you to really optimize your catalyst for the preferred choice of product and better yields. So this slide shows the product formation at a different temperature. You can see the C3 is actually of high yield at 240 and 260, and C4 is around like 250. Then C5 is at 240. Okay, so we can also see the overall conversion of this carbon monoxide into C3, C4 hydrocarbons together. So the maximum yield or the conversion is happening above 230, and particularly at 240 is the optimum condition where you can get the better yield, also the product ratio. So once you hit this catalyst above 260, you see these hydrocarbons are disappearing, and you see the increase in carbon dioxide and water. Okay, so you can also study the methane yield. Okay, so that means from the TIC, you can get the extracted ion chromatogram. Okay, which will allow you to see the peak height or the peak area for methane, from which you can calculate its yield. So for this case, we have used the analytical column of HP plot Q. Okay, it's a 30-meter length and the ID of 0.32 mm. So as you know, the product distribution can vary depending upon the ratio in which you are mixing hydrogen and carbon monoxide. So here we show how this ratio also can be optimized using the online single microreactor. So when we use of the different ratios starting from 3.5 and until like as low as 0.8, you can see how these products are like different. And particularly you can see the high yield can be observed at 0.8 ratio. However, at this low ratio, you have this coking issue. That means your catalyst will have a lot of carbon deposit, which means you have to decoke more frequently to continue your studies. So for this reason also sometimes we have to choose the temperature at which this carbon deposition is less, even though the yield may be a bit less at that temperature condition. So the point is you can optimize this ratio by using this online a single microreactor, and we choose the right ratio for the product of your choice and preference. Okay, so far I have explained briefly about the Fischer-Tropsch synthesis, also the different type of catalysts that are being developed for the synthesis, where they want to have a better yield and a better like high value product. So whenever you develop such catalysts, these catalysts can be evaluated or screened using this online single microreactor. We can actually accelerate your research because compared to the conventional way of the offline reactors, this can be producing the data in situ, and also you use small amount of catalyst, so you save cost as well as time, which will really help you to accelerate your research programs. So now let me quickly explain what other things one can do with this single microreactor. So as I said, we can introduce a liquid sample and gas samples in this single microreactor. So the Fischer-Tropsch synthesis, where we have shown the use of syngas, which are in gaseous form. Now we show another application where we can use ethanol. Okay. So you pump this ethanol at very small flow rates. Okay, and there is a heater at the top of this furnace, which allows to vaporize this ethanol. Then subsequently they pass through the catalytic bed, and you see the different products distribution and yield. So for this study, we have used the zeolite catalyst, okay, with 20% coating on alumina and the mesh size of 20 over 30 mesh. So this is the catalyst that we have filled in this column, and we have done stepwise heating, okay, 100 degree, 200, 300, and 400. So you can see the objective of this study is basically to see how good this catalyst is for ethanol to ethylene conversion. So we can see the ethylene conversion is happening at 300 and above, and ethanol is also slowly disappearing. And before the ethylene formation, the diethyl ether is the intermediate product, which is very predominant at 200 degrees. So only above 200 degree this being converted into the uh, ethylene. So you can use this data to show the mass change, okay, or the concentration profiling, or the change in ethanol concentration, which is happening at 250, and you can see the ethylene formation, which is actually high at 250, and diethyl ether is basically the intermediate that is actually predominant at 200 degree. So this data can be collected with a single reactor, okay, where you can do a continuous monitoring as well as the stepwise heating with the detailed GCMS analysis. The data shown in this slide, basically the stepwise heating and a detailed GCMS analysis. From this peak area, you can also calculate the mass of this ethanol reduction and also the production of ethylene.
Eh,
Yeah, this is another example
eh,
where we show
aduh.
that, excuse me, yes, yeah, we show another example, catalytic conversion of ethanol into butadiene. So we are trying to see a different product from the same raw material. So for this, we have to consider a different catalyst. Okay, so we are using the magnesium oxide and silica mixture, the ratio of 3:4, and the mesh size of 35 to 45. So this is the catalyst that is filled inside the reactor, and see how this catalyst is performing the conversion of ethanol into butadiene. At the same time, what is the ideal temperature at which we are able to see the maximum yield and good purity products. Okay, so you can see the butadiene formation is actually starting at 300, but the maximum yield is obtained at 400 degree. So from these peak areas, you can also see the kind of the concentration profiling of the formation of ethylene and also the intermediate like acetaldehyde and also the ethylene and the reduction of this ethanol. Okay, so again, this is another example where you can use a liquid sample like organic solvent like ethanol, and you can optimize the reaction condition for any type of catalyst. Same time, the results will also help you to evaluate screen the catalyst for its required performance. So with that, I would like to wrap up this webinar with some concluding remarks. Online single micro reactor allows to evaluate the catalyst, okay, is rapidly, and it also help you to optimize the conditions quickly. So the good thing is you can run these experiments at very small amount of catalyst. Still, the results obtained from this reactor are scalable. So we basically save cost and time by using this online microreactor. So this is useful for evaluating different catalysts when they are developed for different catalytic reactions. And we have shown the use of this single reactor, okay, for evaluating the performance of catalyst for Fischer-Tropsch synthesis and also the catalytic conversion of ethanol. So as I have shown in the first slide, we have another type of microreactor, which is called tandem. So it's basically putting two reactors together. So where the first reactor allows you to treat the biomass at high temperature, then the products from this reactor can be introduced to the catalyst in the second reactor. So which allows you to investigate or study the catalytic pyrolysis products distribution, also the yield. So if you want to know more about our microreactors like single and tandem, please visit our website www.frontier-lab.com. So if you have any questions, please post your questions in the chat box. I will try to answer them.